So we had a ton of requests to do a video on how to build the FA series of Subaru engines, and finally got the opportunity to show you on an engine that I think is worthy of us doing a video on. Now, this engine is for like pretty moderate horsepower. I would say that it could probably take about 500 horsepower. The FA engine in base is a sturdier engine than the EJ, and I don't think you have to close deck it or anything until maybe you get into 600s, but I mean there's other problems that you have to address if you're going that high besides just getting the closed deck, but it is pretty sturdy. So that being said, let's start with the bottom end and what we're doing to make this bad boy strong. So starting off, we're using the stock crank. The stock crank is actually a pretty sturdy piece. I know in some of our EJ videos, people have commented about how wimpy the crank looks, but that's not really true. I mean, the crank is short, which helps stiffness. It also has a lot of journal overlap. If you look here, you can see the main and the rod journals have overlap in the center. Now this greatly helps strength and stiffness. Also, the journal sizes are pretty generous, so there's a lot of support for the crank, a lot of bearing area for like boost pressure and things like that. Other things that are pretty cool is the oil holes are chamfered, and they have these little reservoirs in them from the factory. And this is the thing that we have to do on a lot of cranks, but on the Subaru, it comes like that from the factory. We get the crank, we micro polish it, and in this case, we send it to CTP Cryogenics to get it cryogenically treated. The cryogenic treatment stress relieves the crank and also converts the austenite, which is the crystalline metal structure, to martensite. So we're going from a face-centered cubic to a body-centered cubic structure. It's martensite is harder and stronger than austenite. So we're there's some martensite in the stock crank, but we're converting more of the austenite into martensite and improving the strength. It's kind of like heat treating. So think of cryo as an extension of the heat treating process. Like a lot of people say it's snake oil, but there's science behind it, and I just told you, I guess. So after cryo, micropolishing and cryo, then we set it out to be WPC treated. WPC treatments like this Japanese micropeening process where the surface is shot at high velocities with super round, really small ceramic balls that kind of look like talcum powder. And with this media, they also put like dry film lubricant stuff like zinc and moly, and they're kind of secretive about the exact constitution of that, but what it does is it kind of forms a hard skin over the surface of the part, and also impinges dry film lubricant into the surface, and it also puts a micro dimpled surface and kind of refines the surface so it's super smooth, super lubricious, super low friction. So the hard skin helps prevent micro cracking from propagating in the surface of the material to turn into big cracks, like as you get some fatigue going on. So WPC generally increases the fatigue strength of a part by about 100%. So this isn't tensile strength, but it's more like the amount of cycles before failure kind of strength. So that's improved about 100%. So WPC reduces the likelihood of cracking, helps fatigue strength, reduces friction. So it's a winner all around. The crank is nitride from the factory, which also puts kind of like a hard skin over the surface, makes the journals more wear resistant. That's all good, but that's a factory thing. We precision balance it. The balance is pretty good from the factory, but we take it to the next level. And other than that, it's a stock crank. The crank can probably hold 800 horsepower, but there's other things that are not going to do too well in the engine before you hit that point. So that's the crank. Next, we'll go to the pistons. So if you're a Subaru fan, you know the piston is the Achilles heel of EJs. Like the EJ has a big bore, a short stroke, and with the big bore, you have a lot of crevice volume around the top of the piston in the area between the top of the piston and the number one compression ring. This acts like a trap that stores hydrocarbons, and these hydrocarbons can be released into the exhaust in an unpredictable way as basically raw, uncombusted gas. This makes your HC emissions go up. So to pass our stringent emissions on the EJ, Subaru moves the number one ring really high on the piston, and that makes the piston really fragile, and it breaks ringlands, exposes the number one ring to a lot of detonation force. This is probably one of the major causes of EJ going bye-bye is the failure of the ringland. But on this engine, it only runs like an 86 bore or the 86 stroke, which is the same as a lot of popular 2-liter engines. With the longer stroke, it kind of helps with torque. With the smaller bore, the ring crevice volume is less, so the factory can move the ring further down the piston, and the piston is more sturdy. This is a performance piston that's moved down even more, so you have a really strong piston. Now, this is a Manley piston. It's for the direct injection, the FA20D DIT. One of the things that you got to consider with direct injection is you basically should copy the pre-chamber shape that's on the stock piston on your modded piston. The pre-chamber is this guy right here. So the direct injector fires right into here, and this little bowl acts like a trap, so it keeps all that fuel air mixture like right around the spark plug, so it ignites easy. Direct injection is really awesome. Like, it allows you to be turbocharged but run a pretty high compression ratio. Like the EJ is, the compression is in the 8s, depending on what variant you have. But the direct injection engine, it's 10.6 to 1. So that really makes things more snappy. It helps fuel economy, helps spool the turbo quicker. If you ever drove an FA, they're like fun, zingy engines, not much turbo lag, and they actually feel a lot faster than their horsepower would suggest, where the EJ kind of maybe feels a little slower than its horsepower might suggest. And a lot of it's due to the high compression ratio and direct injection. The other thing about direct injection is it puts the fuel right around the spark plug area. And so you don't have to worry about as much fuel getting into the crevice area. And that's another reason why Subaru is able to lower the ring package on the stock piston to make a stronger piston. Like if you're making custom pistons, you want to copy this geometry because, like, let's say you did a flatter top, the direct injector might just fire and blow the gas right out the exhaust port. You can see in the cylinder head, the direct injector kind of fires straight across the piston. So you kind of need this like feature here to, try to keep the fuel from going out the exhaust port and overlap. This Manley piston is made out of 2618 low silicon alloy for a turbocharged engine, especially if you're running a lot of boost. This is probably one of your best choices. It's tough, ductile, it's really hard to like shatter and crack. You might see my other video where I'm hitting one of these with a hammer compared to a cast piston. And the 2618 piston took a pretty big hammer blow that cracked the cast piston. One of the drawbacks about 2618 is that it expands more with heat. So you have to run a little bit bigger piston-to-wall clearance. So your piston skirt design is really critical if you want an engine to be quiet, not rattle around, not burn oil, and have a long life. So Manley has pretty good skirt designs. We've run these pistons before, and they're not that noisy. some other brands that don't have as good computer simulation in their design. Their 2618 pistons are noisy and they can create false knock with a knock sensor and cause tuning issues, but not these suckers. It's a pretty sturdy piston. There's a really big #1 ringland. It has a pressure equalization groove. This acts like a pressure reservoir between the first and second compression ring to kind of helps the second ring get a little bit more tension and hold itself to the cylinder wall better, so the overall seal gets better, especially at high RPMs. They're all low tension rings. The oil ring is a low tension narrow rail. It has a lot of drain back holes, so all the oil getting scraped off the cylinder wall can like dump it back in the crankcase without much resistance. Overall, it's a pretty cool piston, and like all Manley products, it's a really good piston for the money. We pretty much leave the piston alone, but we WPC treated it in this case. And the advantages on aluminum with WPC is just like the same as the crank. So next we're going to talk about the connecting rods. On the FA motors, the connecting rods are probably their Achilles heel. When you're tuning them, if you run above 330 foot-pounds of torque, and for sure if you run above 350 foot-pounds of torque, you tend to bend the rod. This usually isn't a catastrophic failure, and if you catch it, you could usually save the engine, but bending the rod isn't cool. So it's really important to get good rods in these motors. The rods have this kind of weird offset in them, as you can see, and that's so you could, when you're assembling it, the engine, you can tighten the rod bolts. It's really apparent when you're putting one of these together, but that's why the rod looks strange. So we're running a Brian Crower rod. This is a really nice, strong part. It's made out of high nickel, high molybdenum steel, so it's like 4340. It's a real tough, ductile steel with a high tensile strength. It's one of the best things for rods. The toughness is good for repetitive high stresses, like a connecting rod sees. It has like some interesting features. Like one of them is the ribs across the small end of the piston. This really increases the strength of the small end, and the small end is probably the second highest stress part of the rod. It has ARP 2000 bolts, and the whole rod is shot peen. Shot peening also increases the fatigue strength by 100% to 200%. It's a fairly aggressive shot peening, so I think it probably makes a pretty big difference. Another thing is like on the thrust faces of the rod, Brian Carr put these notches so oil can get down in there, and then oil can circulate as it comes off the rod bearing and kind of lubricate these thrust faces. Not too many rods have that, and I actually think that's a kind of cool feature. There's a bronze bushing, silicone bronze. There's an oiling hole at the top. Sometimes I think that's not the best thing, but these strengthening ribs more than make up for it. So this is a good rod. We don't need to do too much to it. Basically, we precision balance it. The weights are pretty close on these from Brian Crower, but with our precision balance, we get about dead nuts. Then we cryo treat it and WPC treat it for the same reasons. We also WPC treat the threads of the bolt and under the bolt heads, which helps the fatigue strength of the bolts. And as you know, the bolt is like one of the highest stress part of the engine and one of the most common places to fail. So the WPC helps all that really good. But it's a high quality rod. We don't need to do a whole bunch to it. You look at the piston rings. Basically, the rings are like any other performance ring nowadays. The #1 ring is a steel ring for strength and resilience. It's nitrided for wear resistance. It's really thin, low tension. The number 2 ring is ductile iron. In the case of these Manly rings, it has like a plasma coating on there. Uh, the iron helps it seat quickly. The plasma coating kind of helps the overall wear resistance. It's on the top and the bottom a lot, so that kind of helps the wear in the grooves of the piston, which is important for seal. Um, they're all thin, low tension. The oil ring is like also thin and low tension. So it's your typical state of the art for nowadays ring set. The bearings we're using King XPC bearings. Now we really like King, but conversely, if King's not available, we like ACL or we like Cleveite bearings too. So these bearings are a tri-metal type. So you have your base steel, then you have your load-bearing surface. They used to be made out of mostly lead, and a lot of stock bearings are still like really soft, like zinc and aluminum. The King bearings are kind of lead, and they're hardened with tin and antimony and copper. So it's a really hard substrate compared to OEM bearings, for instance. So it has a much higher load bearing capacity before like it mushes out and you spin a bearing or something. The disadvantage of this kind of hard substrate is that it's not good for embeddability. So if you're the type that never changes his oil, they're maybe not the best choice. But I know all of you performance guys change your oil a lot, and you would rather have a stronger bearing. I know I would. The bearings are coated with like a polymer coating, so it's not Teflon, but kind of like a Teflon, and it has molybdenum and slippery stuff in it. It also has copper nanoparticles. Now, traditionally, like the top coating is like a quick zinc plate, which kind of is soft, kind of helps embeddability, kind of helps the bearing burnish in when you're breaking it in. But it really can't take much load or anything, and it doesn't really help the bearing's load capacity. But the XPC coating, especially with the copper nanoparticles, actually can bear load. So it's soft because it's kind of plasticky. It has the lubricant particles in it, but it also has the copper particles, so it actually helps load capacity, unlike any coating that I'm aware of currently. It's one of the reasons why we like to use it. So King main bearings, King rod bearings. The main bearings also have some kind of neat features, like the oil transfer holes are chamfered. They also are ovalized for more area, so they act like mini reservoirs to kind of help lay down the oil into the bearing space and line up with these holes better and have a little bit more dwell time for that. These are some of the things that we might hand do to some bearings, but with King, it comes like that. So it's one of the reasons why we really like that bearing anyway. As far as like case bolts, we use ARP. So when you're running these ARP bolts, one of the things you got to remember is they have more tension. They don't have stretch like the stock bolts. They have these hardened precision ground washers, so the torque can be really precisely applied. When you're running these bolts, it's really important to, like check the align bore on the cases and, like do a hone on the bores with a torque plate and all the fixturing. Because Subaru cases aren't that strong, even these newer ones, and you get some distortion. And so if you do your honing properly, you can straighten that back out and still, have good piston seal and good ring seal and not scuff or anything like that. So really important when you're running the stronger hardware. Be sure to check your align bore and be sure to do your honing with the torque fixtures. That's what we do. That's kind of how we do the bottom end. when we're talking about our cases, the FA cases are a lot stronger than the EJ257, for instance. When you look at it, it's pretty clear. The cylinders are thicker. The edges of the case where the head gasket sits is thicker. The head gasket has a lot more support. There's these buttresses that go all the way to the bottom of the water jacket. One of the reasons why the EJ fails is that it's either total open deck or the 257 has these like really wimpy little bridges that go across, and they're like maybe only 1/8 of an inch thick or something, and that allows the cylinder walls to flex and move around, which isn't good for much, and it tends to be hard in the head gasket too. But you look at the FAs, there's these really thick buttresses that go all the way to the bottom of the water jacket, and they come almost to the top of the cylinder. The reason why a lot of manufacturers are going to open decks nowadays is you get even heating of the bore, so that means less bore distortion, better ring seal, less distortion, less friction, better ring seal. When there's better ring seal, there's less emissions. When you get even heating of the bore, especially across the top where the fire's at, you keep that crevice volume hotter and you have less hydrocarbon emissions. So less emissions is one of the big reasons why so many manufacturers go for open deck nowadays. But you look at the FA, you got a lot of support just below the deck with all these thick buttresses. So, you get your open deck, but you still get like a lot of stiffness that you don't have in the EJ. One of the things we do is, which is another kind of Achilles heel on these engines, is they tend to not oil super well. And one of the reasons is that it has a non-priority feed for the main bearings. So when the oil comes off your oil pump, it goes into the main oil galley passage right here. And it goes all the way through the case. Half of the oil goes to your mains, and the other half goes to your heads. The ideal way is to have the full pressure of the oil pump feed the main bearings, and excessive oil will bleed off to the heads. So that way your mains always have the full pressure that the pump puts out. Now, it's not only Subaru that has non-priority mains, like probably almost all production engines nowadays are like this, but it's one of the reasons why these engines sometimes get bearing problems. In my opinion, the bearing problems could start to manifest around 450 horsepower. This is like if you're road racing on the track, and if you're doing occasional blasts, or it's a street hooning, or it's a drag car, you're probably not going to see it. But if you're doing track days, time attack, road racing, you may, if you start exceeding 440, 450 horsepower. So for oiling mods, Killer B makes a heavy-duty pickup for the FA20, and it has a stronger screen, and the screen is actually swedged in there, and it's a little bit bigger diameter. So the bad thing about the stock pickup is the screen can be easily punched in, so it could actually punch in, get into the pump, or it could fall out. It's really weak. That's one of the weak points of the stock pickup. Also, the Killer B one has more volume, like right under the screen, and a bigger tube. And one of the bad things is the pickup tube on the FA is actually smaller than the inlet on the oil pump. So the pickup tube is a restriction. The Killer B one is going to help. On our particular motor, we're going to use a IAG pickup and baffle. Now the IAG one is like the Killer B one, probably works about the same. It has like a cast piece right underneath the screen that actually has a higher volume and maybe is a straighter shot into the tube, but the tube has a slight bend in it. So it's Probably about equivalent. It's also like bigger ID and bigger diameter, really strong, so it's not going to break like the EJ tube. Now the baffle goes into the upper pan, and it has one-way trap doors to prevent the oil from splashing up. It's why you really like this pan. Like some other companies like Greddy makes the same thing, but it uses louvers, and it's not as positive sealing as these flappers. Now the FA does have a stock windage tray. It's not in here. It actually bolts to here, and so that helps strip the windage off the crank. One of the cool things about the FA is that the EJ just dumps oil right onto the crank and everything, and it makes more windage. But the FA actually gets the oil from the heads, and it goes through these passages here, which goes to these passages here, which goes to these tubes on the pan. So the oil actually gets reintroduced right at oil level. So none of that stuff gets dumped on the crank. So there's a lot less windage going on, and like how EJs have the problem with puking oil. So the FA should be a lot better. So this pan is kind of a smaller volume, but it doesn't include the fact that this has an upper pan. So the pan's two-piece. This goes in here. This bolts onto here. And the lower pan goes on like this. And so all the oil is going to be contained around here with this good pickup. So it's going to have decent oil control. It's not like the EJ where it can like just splash around. If you have an FA24, IEG also makes a baffle and a pickup for you. Or if you have a BRZ FRS FT86, they make one for that too. If you have an FA24, Killer B also makes a horizontal baffle that prevents the oil from going into the timing chain area. So if you have the IEG baffle and that'd probably be pretty good oil control. Now if you have a FA, sometimes if you rev them past maybe 8,000 RPM a lot, they break the oil pump gears. So Tomei makes some billet gears. Now like if you have a turbo motor, I don't really recommend that you spin it that hard, and I mean you can make a lot of power spinning to the factory rev limit of 7,700, but let's say you have a belt NA one and you're going to wind it out, better replace those gears. Some of the things we do to address the oil feed issue is, so this is like your oil pump cover. You get the output of the pump, and it goes to this passage to feed the main galley. But what's weird on this motor is this passage is really small, and it's a lot smaller than the galley. So what we do is we bore this out so it's the same diameter as the galley, so it doesn't act like a restrictor. Subaru puts a really nice radius in it from the factory, so the oil can make a nice smooth turn, but we bore this out to the same diameter as the case. And then we also chamfer the lead into the bore so we maintain that nice smooth factory radius. I think that helps flow quite a bit. I don't know what Subaru was thinking and why they necked this down, but it's something that I feel like helps, and it's easy to do. Other than that, it's pretty straightforward. The block or cases are stronger than the EJ. This engine's a lot less finicky and has more overhead for for bolt-on mods and tuning without braking. So for our cylinder heads, we didn't do extensive CNC porting or anything. You can actually make pretty big gains with just some simple, I guess, tricks. The first thing we did is we did a Neuen valve job. Now a Neuen valve machine is not like a Surdy or something that has cutters with 3 angles where you just plunge it down, and you get a 3-angle valve job. What a new one is, it's actually like a CNC machine where you program the cutter, so the cutter will come in and do a smooth, perfect radius to your 45 seat, and from your 45 seat, it'll make a smooth radius into the throat of the port. Now, this does a lot of stuff that like hand porting a head would do, and it picks up a lot of flow and a lot of power, especially low lift flow. Low lift flow is the most important because your valve spends the most dwell time at low lift. For instance, like you're at low lift twice and you're only at max lift once. That's a simplistic way to look at it. Also, the way a cam's acceleration ramps are, you spend a lot of time when the valve's opening to avoid shocking the drivetrain, if you have a cam that's designed any good anyway, and you set the valve down slowly too. So the valve spends a lot of time around the low lift part of its curve. So that's why low lift flow is important, and what we do makes a pretty big difference. You can kind of see this smooth blended valve job that's one continuous thing almost. The seat is still like a 45, and the seat width is still wide enough to do the job. If it's a turbo motor like this one's going to be, we make the seats a little bit wider. This helps pull some of the heat off the valve. Also makes a longer lasting seat with a hotter running turbo engine. So once we get this new valve job, one of the options that we do is we hand blend the valve job into the combustion chamber and the port. So we get die grinders and cartridge rolls, and we blend the valve seat itself like right at the base of the new cut and kind of blend it into the port. And this kind of opens up the bowl and really helps flow. We also get the top new cut and we blend it into the combustion chamber. This reduces valve shrouding and just makes an additional smooth area so the stuff can go in and out of the chamber really well. Now this stuff gives you about 80% of the flow of your typical CNC port job at a fraction of the cost, and we like it in all motors. Mostly if you're going to be running forced induction or a turbo, that's all you really need to do. Maybe a NA car would benefit from full porting, but if it's any kind of mild kind of build that's good to see street use, this is probably enough. It makes a pretty good difference, and it's worth doing. For valves on this particular engine, we're running GSC valves. A lot of times, we'll use Ferrera or we'll use Supertech. Our customer wanted GSC, and there's nothing wrong with them. We like them too. These are like stainless valves, and they kind of use an exotic stainless steel from Carpenter Mills. Now, if you're a gun geek or a knife geek, you know all about Carpenter steel and how it's badass. So the alloy they use is for the intake, it's a austenistic stainless with nickel, molybdenum, and chromium in it. Pretty good valve, not too abrasive on guides and stuff, and really strong. For the exhaust valve, it uses a special alloy that Carpenter makes, and it has a lot of nickel, a lot of chromium, and a lot of molybdenum in it, probably about twice the level that the intake valve has, and this makes it really hard, erosion resistant, and heat resistant. So it's not Inconel, but it's still a sophisticated metal. Should be really good and should last a long time. Other features on these GSC valves that are pretty cool is they do a flow analysis. So on our other engines, we talk about how we usually like a flat nailhead contour on the intake valve, and that helps flow going into the engine. And the exhaust valve, we like a nice tulip kind of contour, which helps flow coming out of the engine. There's swirl polishing, which perhaps might help flow at low lifts. It's kind of debatable, but I guess, it looks cool too. I mean, it probably fills up with carbon right away, so, but it does have swirl polishing. Another cool feature is that the tips of the valves have like stellite, which is a really hard material, bonded like with diffusion bonding or something to the tip of the valve for wear resistance. It's a really cool valve. We're also running GSC silicon bronze valve guides, so these have a lot of lubricity. They're easier on the valve stem and they last longer than the stock iron valve guides. And we're using GSC valve seals. Instead of just being made out of rubber, the GSC seals are made out of Viton. So if you're an engineer, Viton's a fluoroelastomer, sort of like a synthetic rubber, but it's extremely heat and abrasion resistant. It's probably one of the best things for a valve seal. For the valve train, we're running Kelford 264A cams. Now, I don't remember the numbers exactly, but they're pretty appropriate for a mid-power level engine. I think the duration is 272 degrees on the intake and maybe 278 on the exhaust, and there's 11.8 millimeters lift, which is kind of a lot for these small 4-valve engines. What I like about Kelford cams is they really have the science of their kinematics or the valve train down, so they tend to have more area under the lift curve per degree of duration than any other cam in the import market. So Kelfords, have more area, more flow, make more power without some of the disadvantages of having a lot of duration, like low P idle and poor fuel economy. So for the lowest duration numbers, they have the most area under the curve in general. Also, they have their valve train kinematics down. So, they study the harmonics and stuff, and they study the harmonics up to like pretty high order, because a lot of your spring surge and stuff is caused by fifth and sixth order harmonics. Spring surge is what people call a valve float. Engineers, we call it spring surge. But by controlling the excitation with the cam ramp contour, you could like passively get a lot of float resistance or surge resistance without resorting to super high valve spring tensions. Valve springs are running a Kelford dual spring and a titanium retainer. I'm a big proponent of running the exact valve springs that the cam manufacturer recommends, because if you have an engineering intensive cam like a Kelford, the harmonics of the springs are considered for the profile of the grind. So, anything that moves, has a natural frequency. So the natural frequency of the spring package is, and the ramps of the cam are tailored not to excite everything to get surge or valve float. So stick with the springs that your cam manufacturer recommends. I mean, that's what I'm a proponent of. So nice cams from Kelford. So another cool thing is that we're going to be running this Nordstrom high pressure direct injection pump. This pump has about 40% more volume than the stock pump, so you have fuel headspace for the additional power. The other cool thing is that the OEM Subaru pump doesn't tolerate ethanol very well, and guys have been having trouble with the stock pump seizing up and squeaking and things like that if they're running more than like maybe M50. For some reason, the OE pump doesn't tolerate that, but this pump can eat E85, it can eat pure ethanol, no problem. And it could also provide enough fuel volume for all that. And it has enough fuel volume, I think, to make about 700 horsepower. So that's more than enough to blow the bottom end apart. So it's a good deal. The last thing we do is that generally we like to run a fluid damper on these flat engines. they have some weird vibrations, and the fluid damper works to damp that out. I've always been a big proponent of fluid dampers because the harder things whip, like in the crank and all that, those damaging vibrations that can kind of throw even your crank angle sensor off and cause spark scatter. This works actively to damp it out. So the more your crank whips, the harder this thing works. What it is it's a floating inertia ring. You see that right here. And it's inside this welded housing. The inertia ring's free to move. So unlike a conventional damper that the ring is constrained by rubber O-rings and it's tuned for only a certain frequency of vibrations, with this being free to move, the higher the amplitude of torsional whip, the more damping it provides. So it works for a broad RPM range. So I've used these on EJs, like the FRS. It's a pretty cool thing. The damping is done by this silicone goo that fills up the housing. Now you see here there's a ball bearing, and I flip it upside down and the ball bearing's barely moving. So that gives you an idea of how thick this stuff is. I mean, it's like super thick honey, I guess. And this is a silicone fluid. It's pretty stable across a pretty big temperature range. Doesn't shear down. So this thing will last the lifetime of your motor. And maybe you can put on several different motors after. It's not like a conventional damper that has like a rubber holding the inertia ring on there. The rubber deteriorates and even comes apart with time. Silicone, it's good to go for life. So on EJs in particular, you can actually feel the difference that these things make, and FAs. So I think that about wraps it up on the FA. I pretty much like this motor. It's kind of fun, responsive, feels like it punches more than its weight. It's zippy and responsive. It's stronger, bone stock, and can tolerate tuning a little bit better than an EJ. It still has its weak points, but we're addressing them. So, it's kind of fun to build one of these, and this is going to be a really fun motor to drive, and it should be nice and reliable. So if you like this video, please depress the subscribe button and follow us. We have an online store, so we sell a lot of these parts that we talk about in our videos. You help support us. It helps us get the money to create more content. If you want to get some cool MotoIQ swag, we have that on our web store too, so you can get a sick hoodie like this and a cool MotoIQ shirt. If you don't want to look like a MotoIQ billboard, we have some other shirts too that are kind of funny. So go ahead and take a look at those. If you want us to build you a motor, you can go to MotoIQ.com, our website, and hit the garage services link and fill out the form, and we can get you a quote. If you like tech content and you still know how to read, you can go to MotoIQ.com, and we literally have thousands of tech articles on there, and you can probably read to your heart's content for a couple of years or something. So I hope you enjoyed this video on the FA20. The FA24 is really similar. We haven't built one yet, which is probably a good sign. That probably means they don't blow up too much. And the features are mostly the same. The biggest difference is the bore size. So until next time, we'll see you around.